Diels-Alder reaction with a cyclic diene. So as you've been working through example problems in your textbook and maybe from other videos, you might have noticed a lot of Diels-Alder reactions occurring with cyclic dienes. So where you have your diene system that's within a ring. And so why is that? If we take a look at this ring system, what we're doing by putting this in a ring is we're essentially locking the diene into the S-cis conformation, which is the reactive conformation for a Diels-Alder reaction. So if you have a cyclic diene, that diene is locked in the S-cis conformation. And so since it is already locked in that reactive conformation and it doesn't need to rotate, that means that this is a more reactive diene for a Diels-Alder reaction. And so that's why we see a lot of examples. And so the cyclic diene that I chose here is cyclopentadiene. And cyclopentadiene is actually so reactive that it undergoes a Diels-Alder reaction with another molecule of itself. So you actually can't buy cyclopentadiene. You have to buy it as the dimer. It's dicyclopentadiene. And then you have to heat it up and distill it in the lab to get the retro Diels-Alder to take place. Okay. And that's not a detail you need to know. It's just kind of a fun fact about how reactive it is. All right, so whenever we're trying to draw the product of a Diels-Alder reaction, we want to locate the 6 carbon atoms that are involved in the reaction. So remember, here's your diene. You need at least 1 pi bond in your dienophile. And this reaction is always going to give you a 6-membered ring with a pi bond between carbons 2 and 3. So I will number these. And we can draw in the arrows. So this is a cycloaddition reaction. And it always occurs the same way. So it's really predictable in terms of coming up with the product. So what we would do here is number the 6 carbon atoms that are involved. So find your diene and number that 1, 2, 3, 4. Your dienophile is 5 and 6. And then when you're drawing the product, you're going to start by drawing that cyclohexene ring. Use the pi bond to locate carbons 2 and 3, and then number from there. And finally, any substituents that were attached to these 6 carbon atoms need to still be attached in the product. So for the diene, we've got a 1 carbon bridge between 1 and 4. So we're going to draw in that 1 carbon atom bridge. And then on carbon 6, we've got this methyl ester. So we're going to draw that in. And finally, we do need to also include the stereochemistry. So we want to make sure we are following what is known as the endo rule. And the endo rule tells us that the endo product is typically the major product. And this is actually a gross simplification, but as beginning organic chemists, it's fine to start here. We just need to know how to draw the endo product. So the endo product tells us that our bridge is going to point in one direction. And your substituent from your alkene will point in the opposite direction. So the substituent from the dienophile will point in opposite direction. So what we can do here is we can just shade in this bridge so that it's pointing up. And we will indicate that this is pointing back. And you could also see this drawn in 3 dimensions. You might see, here's that bridged system. So this is carbons 2 and 3. We find that pi bond, 4, 5, 6, and 1. And see the bridge is pointing up. Here it is pointing up, and I want this on carbon 6 to be pointing down, so I would put it down. And those two structures are equivalent to each other. So you should be used to seeing it either like this or like this. Now, the reason behind the endo rule has to do with the stabilization of the transition state that leads to this. And so if you want to see that transition state, it is in your textbook on page 360, if that would help you visualize this. But what you really need to know is simply that this will be the major product.